So in the previous module, I was talking about applying HMO approximation to a 3-electron system, that's allyl system, and we obtained the bonding molecular orbital, anti-bonding molecular orbital and non-bonding molecular orbital wave functions. We also obtained the energy values of the system, energy of these molecular orbitals, and I said you that allyl could be allyl cation, allyl free radical, and allyl anion, depending upon the number of electrons which is present in the system. So a quick recap of what we did. If I go back to the hydrogen to the energy level diagram, then I think this was the energy level, energy of the system. Okay. So you have alpha plus root 2 beta, alpha and alpha minus root 2 beta are the three energy levels. Okay. So if you and in the bonding molecular orbital, if you have cation, then you have 2 electrons which fills the bonding molecular orbital. If you have anion, then you have 4 electrons. So 2 are in the bonding and 2 are in the non-bonding molecular orbital. And if you have free radical, then you have 3 electrons. So 2 electrons are in the bonding and 1 electron in the non-bonding molecular. Based on this, so if I write here cation, anion, free radical, just for the sake of recap, anion, if I write, then cations have 2 electrons which is present in the bonding. In free radicals, you have 2 electrons in the bonding and 1 electron in the non-bonding, and in case of anions, you have both these system occupied by 2 electrons. So with this knowledge, we can calculate the electron density, charge density and bond order of the system. Okay. So as you are aware of, what you do, allyl, we will first look at the allyl carbocation, where only 2 electrons is present and that both of electrons are in the bonding molecular orbital. So the bonding molecular orbital, if at C1 you find these are the coefficients of C1, these are the coefficients of C2 and these are the coefficients of C3. In case of non-bonding molecular orbital, you have the coefficients for C1 and coefficients for C3, and the coefficient for C2 is 0. In case of anti-bonding molecular orbital, you have the coefficients of C1, you have the coefficients of C2 and you have the coefficient of C3. Okay. So what you have to do for calculating the electron density, number of electron multiplied by the coefficients of that carbon, C1 carbon, a square. So 2 into 1 by 2 a square, it will be 1 by 2. Okay. So 1 by 2 is the charge present on the carbon number, electron density present on the carbon number 1. With an electron density at C2, again number of electron multiplied by the coefficients of the, because we have only 2 electrons and which is present in the bonding molecular orbital. So we are, for calculating the electron density, we are concerned with Psi1 only. Psi2 and Psi3 will not play its role, because for carbocation, Psi2 and Psi3 are vacant. Only the electron present is in the only bonding molecular orbital. So 2 multiplied by second carbon atom coefficient is root 2 by 2 whole square. So this comes out to be 1. And for third carbon atom, we have the coefficients 1 by 2. So again, if to calculate the electron density Q2, then it is 2 into 1 by 2 a square. So that comes out to be 1 by 2. So if we have the electron density, then we can easily calculate the charge density. And what is charge density? Charge density is 1 minus Q1. For at C1, charge density is 0.5. At C2, E2, zeta 2, 1 minus chi2 is equal to 1 minus 1, 0. At C3, you have charge is equal to 0.5. So if you sum these two together, what you have charge? You have charge plus 1. And since it is a carbocation, so it is expected that the system will have plus 1 charge. So that's the beauty of HMO coefficients, that even after the such drastic approximations, the result which we get are exactly which is expected. Okay. So we get plus 1 charge present on the carbocation. If you have to calculate the bond order, how do you do this? say bond order between C1 and C2 you have to calculate, and only 2 electrons are present and both the electrons are present in bonding molecular orbital. So what you need is the coefficients of C1 and C2. So coefficients of C1 and C2 are 1 by 2 and root 2 by 2. So 2 multiplied by 1 by 2 multiplied by root 2 by 2, and what the value will come out to be 0.7. If you have to calculate the bond order between C2 and C3, then also you have 2 electrons. So you need the coefficients of carbon number 2 and carbon number 3 of the psi1 wave function. So psi1 wave functions have root 2 by 2 and 1 by 2, and so if you put that value 2 into root 2 by 2 into 1 by 2, it's also 0.7. Okay, bond order we calculated. So we calculated electron density, we calculated charge density, we calculated bond order for allyl carbocation. What about the other? Allyl carbon free radical. If you have allyl carbon free radical and if you want to calculate electron density at C1, then now in this system you have 3 electrons. 2 is in the bonding molecular orbital and 1 is in the non-bonding molecular orbital. So at C1 you have to calculate. So both psi1 and psi2 coefficients of C1 will play its role. In case of psi1, the bonding molecular orbital, 2 electron is present, so the number of electron is 2 and the coefficient is 1 by 2, so 1 by 2 square. In case of non-bonding molecular orbital, only 1 electron is present, so the coefficient is of C1 is 1 by root 2, so 1 by root 2 square, and the value comes out to be 1. Okay. Electron density at C2 if you want to calculate, then Q2, and again you have 2 electrons in the psi1, and so root 2 by 2 is the coefficients of second carbon atom in the psi1, and in the psi2 you have only 1 electron and psi2 has 0 coefficient, so this will go, and again you get the value of 1. If you calculate electron density at C3, Q3, then it comes out to be 2 electron in the bonding molecular orbital, so 2 into 1 by 2 square. 1 by 2 is the coefficients of third carbon atom in psi1. Then 1 electron and multiplied by the coefficients of third carbon atom in psi2, that's a non-bonding molecular orbital, so 1 by root 2, and this comes out to be 1. Okay, and if you calculate the charge density, then for all the charge density will be 0 because it's 1 minus q1, so it's equal to 0, 0, and that is expected for carbon free radical, that the total charge should be 0. So that we get a total charge of the carbon free allyl carbon free radical is equal to 0. Okay. If we go for calculating the bond order, then again the bond order also we can calculate C1 and C2, and now the thing is that you have 2 different orbitals in which the electron is present. So both these orbitals coefficients you will have to count. In the first case at C1 you have 2 electrons present, and so C1 and C2 bond order you have to calculate, and this you should be always with you. This should be C1 and C2. So C1 and C2 you have here also, and C1 and C2 you don't have here. Okay, so you will see that we will not write the, if you go for bond order, look at this one. So you have 0 because in this second non-bonding molecular orbital electron you do have C1 coefficient, you have C2 coefficient is 0. For psi1 you have C1 coefficients also, C2 coefficients also. So the value comes out to be root 2 by 2 bond order. Okay. Then for C2, C3 again the bond order comes out to be root 2 by 2. Okay. So both bond orders we calculated. Now the next system is allyl carbon ion. In allyl carbon ion, what is expected? It is expected that the total charge present on the system should be 1 negative charge. Okay, that's very expected because it's carbon ion. Let's see if we calculate through HMA, we get it or not. So electron density at C1 if you calculate, it comes out to be 1.5. Okay, electron density at C2 if you calculate, it comes out to be 1. Electron density at C3 if you calculate, then again it comes out to be 1.5. And what does it mean? If you calculate the charge density at C1, it will be 1 minus Q1. So 1 minus 1.5 will give you minus 0.5. At C2, it will be 0 because it's 1 minus 1 is 0. And at C3 again you have minus 0.5. So if you sum these two together, you have total charge present is minus 1. and that is expected for an allyl carbon ion. So this is how HMO gives you exactly the similar results which is expected from a particular molecule. Okay. Then we go for bond order. Bond order between C1 and C2, if you calculate this bond order, again you see the C at C2 you have now in this case, in case of carbon ion, you have 2 electrons present in the bonding molecular orbital and 2 electrons present in the non-bonding molecular orbital. So in case of free radical it was 1 because only 1 electron was there. Here in case of carbon ion you have 2 electrons. So 2 multiplied by 1 by root 2 into 0. So it will be root 2 by 2. Then again 2 multiplied by root 2 by 2 into 1 by 2, and again this comes out to be C2 C3 bond order. Okay. So this is all about the allyl system HMO application. When you apply HMO to allyl system, you get the good result for allyl carbocation, allyl free radical and allyl carbon ion. Once we have done the allylic system, means 3 carbon system, now we can extend this concept to a system which is 3 carbon but it is cyclic in nature. So we say such systems are called cyclopentadienyl system. Cyclopropenyl system. Pentadienyl means 5 carbon. So we have cyclopropenyl system, and in cyclopropenyl system you have 3 carbon atoms C1, C2 and C3. They are bonded and they are in the cyclic form. Okay. Now again what we consider here in the case of as in the case of all HMO, we consider this C1, C2, C3 to be sp2 hybridized and one pz orbital present on each of these carbon atom, C1 atom, C2 atom, C3 atom. Okay, and you consider the plane of the board to be the plane of the molecule, and the pz orbital which is present is one lobe above the plane of the board and another lobe below the plane of the screen. So you have pz orbital at C1, you have pz orbital at C2 and you have pz orbital at C3. So your psi MO should be, again psi MO should be C1 psi 1 plus C2 psi 2 plus C3 psi 3, as the case of allyl system, exactly similar to that. Okay. So if you do the variation treatment of this, what do you get? You get 3 by 3 determinant. You get by 3 by 3 secular determinant, and that 3 by 3 secular determinant is like this one, where you know the now since we have done many times, so you remember which is Coulomb integral, which is exchange integral or resonance integral, and which is your overlap integral. So that you know, I will not repeat because I have repeated many times. Okay. So this is your 3 by 3 determinant. Now according to the approximations of Haeckel, what we will write the term in terms of alpha and beta. So in terms of alpha and beta, you get an equation like this one. See, H11 we will write alpha minus E S11 will be 1 because it's a normalization condition. Then H12 is bounded, so H12 is beta, minus E S12 will become 0, so this term will go. H13 is also bounded, okay, so it is beta, and minus E S13 again is 0, so minus E S13 will go, so beta term. 2,1 is also bonded, so it is beta. 2,2 alpha minus E because S22 is equal to 1, then beta, then again S23 is beta, but S23 is again 0, so this term will go, you will have beta. Then H31 is also bonded, so beta, and ES31 will be 0, H32 beta because it is bonded, S32 will be 0, so it is 0, and you have this term as beta. Then H33 again alpha minus ES33 is equal to E. So in terms of alpha and beta, you write this determinant. You have written it earlier also. The only thing is this, that you have to be cautious while writing for cyclic system, because here the nearest neighbor is sometimes not the same, which in case of allyl system 1, 3 was not nearest neighbor. But in case of cyclopropenyl system 1, 3 is also nearest neighbor because they are bonded by a sigma bond, directly bonded. So this you will have to write it cautiously. So in term, and then again you can write in terms of x and 1. If you divide it the whole equation by beta, then you can write this determinant, and then you have to get the value of this determinant. So what is the value of this determinant? X you write, then x square minus 1 this determinant, then 1 is this one, and then you have x minus 1, so x minus 1, then plus this one is here, and then you have 1 minus x, so you get this one. Okay, this is your solution of the determinant, 3 by 3 determinant. And finally what you get, x cube minus x minus x minus x, x cube minus x, then again minus x, this one, then minus minus plus 1, then plus 1, then minus x is equal to 0, and finally it's x cube minus 3x plus 2 is equal to 0. And this could be written as x plus 2 multiplied by x minus 1 multiplied by x minus 1. So what does it mean? The value of x is minus 2 plus 1 and plus 1. Minus 2 plus 1, each of these terms could be equal to 0. If you do factorization, you get this one, and that you can check also. So x could be minus 2 plus 1 and plus 1. So two terms have the same x value, plus 1 plus 1. Okay, and what does it mean? It means that if you calculate the energy, then for minus 2 the energy comes out to be alpha plus 2 beta. For plus 1 the energy comes out to be alpha minus beta, and again you have plus 1, so energy comes out to be alpha minus beta. Okay, so what do you find? E2 and E3 have the same energy, and this is called degenerate state. E2 and E3 are degenerate state. So only 3 out of the 3 molecular orbitals which you get, 2 are degenerate and 1 is the bonding molecular orbital. Okay, for the cyclo-propenyl system, and you can write it like this one. But then again, if you have a carbocation, you will have 2 electrons only, and that will be in the bonding molecular orbital. Okay, so this is a carbocation or carbonium ion, whatever you say. Then you have a carbon free radical where you have 3 electrons. So 3 out of these, 2 will be in the bonding molecular orbital, and any one could be in the any one of the higher molecular orbitals. That are degenerate state. Okay. Then this is called carbon free radical because 3 electrons are present, exactly like the allyl system, previous system which we did. Okay. Then the next system could be a carbon free radical, cyclopropenyl carbanion, and this here you have 4 different electrons. So 2 electrons in the bonding molecular orbitals and 1 electron each in the higher state, each in the higher energy level. Okay, that will be anti-bonding molecular orbital or whatever you say. Okay, actually anti-bonding molecular orbital. So we have carbanion. Now, if you calculate the energy, then what do you get? Energy of the 2 electrons, because of the 2 electrons, is 2 alpha plus 2 beta. Okay, and if both these electrons are present in an ethylenic bond, then what will be the energy? It will be 2 into alpha plus beta. So this is because of energy of ethylenic bond. Okay, alpha plus beta. So as compared to these 2 electrons being in the ethylene, what is the energy which is gained? You see the energy gained is 2 beta. If you compare this energy with the ethylenic bond, then the energy gained is 2 beta, and beta you know is a negative quantity. So delocalization leads to over all the 3 carbon atoms. When it is in ethylene, the electron is localized in between 2 carbon atoms, and when it is cyclopropenyl, then it is localized over all the 3 carbon atoms. Okay, so this stabilization is much higher, and delocalization leads to a stabilization of the system. Okay, in case of carbon free radical, if you do, then what happens? You have 2 alpha plus 2 beta and 1 alpha minus beta, because 1 electron is alpha minus beta also. So together you have 3 alpha plus 3 beta, and then if you minus the delocalization energy, so 2 electron in the ethylenic bond and 1 free electron. Okay, so here the delocalization energy is beta in case of carbon free radical, and then for carbanion, if you calculate, that is 4 alpha plus 2 beta, the total energy, because it will be 4 beta and it will minus 2 beta, so 2 beta 4 alpha plus 2 beta will be the energy. And if you look at both the electrons being in the ethylenic bond, then you have 2 alpha plus beta minus 2 alpha. Okay, then you have delocalization energy is 0. Okay, no, it will be 2 into alpha plus beta. This is missing something. Minus 2 electrons here and 2 electrons here. So it will be 4 alpha and 4 beta. No, it's 4 alpha plus 2 beta minus plus 4 alpha minus 2 alpha will be, so this will go and this will be also go 2 beta and 2 beta. So it's zero energy. Okay. So altogether what you have, 0 stabilization in carbon ion, and if you compare this one, then which is most stable? Carbonium ion is most stable, and then comes the stabilization of carbon free radical. So what you say is that a carbonium ion, cyclopropenyl carbonium ion, is more stable than cyclopropyl carbon free radical, and that's more stable than carbon ion. This is the stability. So what you do in organic chemistry normally, that which of these carbonium ion will be stable, which will not be stable, that also we can go from the HMO calculations, and we can predict the stability of these intermediates. Cyclopropenyl carbocation is more stable because it has the higher delocalization energy. Then you have delocalization energy for carbon free radical is beta, so it will be less stable, and carbon free radical has carbon ion has zero delocalization energy, so it will give you a negative carbon ion. Okay. Now what we say, so this is what cyclopropenyl carbonium ion is more stable than free radical than carbon ion. Okay. The stability of these intermediates we can predict from HMO energy calculations. Okay. Now again we will go back to go back and calculate the HMO coefficients. Energetics we have done, eigenvalue we have done. The next task is finding out the eigenfunction. So for that you need to find out the HMO coefficients, and this was your matrix from which we moved for finding out the energy. So if this is the matrix, then we can write the simultaneous equation. So the first row, what you have, A1 x, and one thing more I wish to tell you, that if you are writing this matrix, this is your matrix, then another, it is actually this one, A2, A3, coefficients are this one, and this becomes equal to 0. Okay. So these are A1, A2 and A3 are coefficients of the wave functions, which you have taken as psi mo is equal to A1 psi 1 plus A2 psi 2 plus A3 psi 3. Okay. And then you get the simultaneous equation when you do variation treatment. Okay. That's a story which we did in variation treatment in details. Okay. So from the first row we can write the equation A1x plus A2 plus A3. From the second row you can write A1 plus A2x plus A3, and from the third row you can write A1 plus A2, because it's 1 1, plus A3x is equal to 0. And from these three equations we have to find out the coefficients A1, A2 and A3 values. So x value we already know, x is equal to -2, +1 and +1. So we first take x is equal to -2 values. And if x is equal to -2, then from the first equation, from this equation, we can write -2a1 plus a2 plus a3 is equal to 0. Okay. Then we can go and write this one from the second equation, a1 minus 2a2 plus a3 is equal to 0. And from the third equation, what you can write is a1 plus a2 minus 2a3 is equal to 0. Okay. So all these three equations with the -2 value we have written, -2 x is equal to -2 we have written. Now if you do a slight changes, a2 plus a3 will be equal to 2a1, that I can write. And if you do this equation for the second equation, what you get, a1 plus a3 is equal to 2a2. Okay. Now if you subtract these two equations, what will happen? If you subtract, this will go, this will go, and you have a2 minus a1. If you subtract, then a2 minus a1, and here you will have 2a1 minus a2, 2a1 minus a2. Okay. And if you rearrange, okay, bring a1 this side, it will be 3a1, bring a2 this side, it will be 3a2. Okay. So you have 3a2 is equal to 3a1, and that means a2 is equal to a1. So we did not get the value, but we got a2 is equal to a1. Okay. Now what you can do, a1 plus a2 plus a3 is equal to 2a1. This is the equation, a2 plus a3 is equal to 2a1, and you have a3 is equal to 2a1 minus a2. You can write 2a1 minus a2. a3 is equal to 2a1 minus a2. a2 should have been there. Okay, no, sorry, it's fine. a1 is equal to a2, so it should be I can write this. Don't get confused. 2a1 minus a2 I can write, and a2 and a1 are same. So you replace this one, 2a1 minus a1, so it will be a3 is equal to a1. Okay. So what you can write is a3 is equal to 2a1 minus a2, and then a1 and a2 are same, so I write 2a1 minus a1. This will, and if you subtract, this will be a1. So a3 is equal to a1. a3 is equal to a1, a2 is equal to a1. What does it mean? It means a1, a2 and a3 are equal. So all three, a1, a2 and a3 are equal. If it is so, then we go for normalization condition. And from normalization condition, what do you get? This we did in the Rayleigh system, this we did in the Thelenic system. So from the normalization condition, we will get a1 square plus a2 square plus a3 square is equal to 1. a1 square plus a2 square plus a3 square is equal to 1. And all these are equal, so the value will be a1 plus is equal to a2 plus a3 is equal to 1 over root 3. So we have got the coefficients for x is equal to minus 2, and for x is equal to minus 2, we have got the energy which is the bonding molecular orbital energy. Okay. So if you do that, what do you get? For bonding molecular orbital, the wave function we can write as 1 by root 3 psi pz1 psi pz2 psi pz3. Okay. Now the question is about the degenerate state. You have coefficients, HMO coefficient for degenerate orbital psi 2. Now for this system, for x is equal to 1, if you want to write, what you can write? The first equation will be a1 plus a2 plus a3. The second equation will also be a1 plus a2 plus a3. And the third equation will also be a1 plus a2 plus a3. So all equations are same. You cannot get the value of coefficients from this one. All three equations are same. Not possible to determine coefficients uniquely from these equations. Obviously, any value of the three coefficients can be chosen provided orthogonality and normalization condition is satisfied. Okay. Now, if all equations are same, for degenerate system, this will always come to you. Okay. So what will you do? One easy way to put one of the coefficients equal to 0. So you have three different coefficients. So put one coefficient equal to 0, and let I put a2 is equal to 0. And if I put a2 is equal to 0, then what will happen? From the equations, a1 is equal to minus a3, that I can say. And if a1 is equal to minus i3, then from the normalization condition, well, that is a1 square plus a2 square plus a3 square, a1 is equal to minus a3. So it will be a1 is equal to 1 by root 2 and a3 will be equal to minus 1 by root 2. Okay. So we have found the coefficients of a1 and a3 putting a2 is equal to 0 arbitrarily, because we have the simultaneous equation which is same, and in that case you have to choose one of the coefficients arbitrarily. But the condition is that the wave functions should fulfill the condition of orthogonality and normalization condition. So if you put this value, your wave functions will be psi 2 will be 1 by root 2 pz1 pz3. For pz2 I have put it equal to 0, coefficient is 0. So here in this case pz2 doesn't appear. Second pz function doesn't appear, only 1 and 3 appears. Okay. If you now, what about the psi 3? That for psi 3 also x is equal to 1. So for psi 3 also we will get the same equation. Now can we choose again an arbitrary function? No, this we cannot do. Coefficients of psi 3 can't be chosen arbitrarily as we did for psi 2. the coefficients of the condition is that the coefficients of psi 3 should be orthogonal to psi 1 and psi 2. Psi 1 and psi 2 we have already determined. Your psi 1 was psi 1 was 1 over root 3. I will write just in simple term P1 plus P2 plus P3. And your psi 2 is 1 over root 2 P1 minus P3. Okay. So these two functions we already have. So your coefficients should be such that the psi 3 which you obtain should be orthogonal to psi 1 also and should be orthogonal to psi 2 also. That is the condition. Okay. And for that, what does it mean? It means psi 1, psi 3 detour should be equal to 0, okay? And psi 2, psi 3 detour should also be equal to 0. Orthogonality condition must be fulfilled in order to get it, okay? If we do this, then what is the psi 2 condition? Psi 2 wave function is 1 by root 2 psi pz1 minus pz3. And psi 3 which we don't know, for which we have to find out the a1, a2, a3 value. So that we can write as a1 psi pz1, a2 psi pz2, a3 psi pz3 and so on. And if you calculate this one, what do you get? Again you see all cross term will go 1 by root 2 a1 psi pz1 detour minus 1 by root 2 a3, you have a3 psi pz3 and psi pz3 detour is equal to 0. Rest of the term pz1 with pz2, pz1 with pz3 will become 0 because the integral will be orthogonal integral, that will be 0. Okay. So the term like psi pz1 psi pz3 detour will be equal to 0. Okay. All terms like this one will become 0. So all cross term will be 0, and so you have, and here this is the condition of normalization. So this will be equal to 1. Here also this is the condition of normalization. So if you bring 1 by root 2 outside the integral and a3 outside the integral, 1 by root 2 a1 outside the integral, then you have the normalization condition. So what you will get? 1 by root 2 a1 minus 1 by root 2 a3 is equal to 0. And so for that we say 1 by root 2 a1 is equal to 1 by root 2 a3, it means a1 is equal to a3. This is the condition which we got. Okay. Now if a1 is equal to a3, then you use the normalization condition of a1 is equal to a3, then a1 plus a2 plus a3 is equal to 0. So what you can write? a1 and a3 are equal, so 2a1 plus a2 is equal to 0 and a2 is equal to minus 2a1. a2 is equal to minus 2a1. From the normalization condition, what you have? a1 square plus a2 square plus a3 square is equal to 1. And so you can write a1 square, then a2 is equal to minus 2a1. So it's 4a1 square, a2 square will be 4a1 square. Then a1 and a3 are equal, so again a1 square is equal to 1. So 4 plus 1, it is 6a1 square is equal to 1. So a1 will be 1 over root 6. And this will be the value of a3. Okay. So a1 and a3 is known now. So a2 you can calculate. a2 is equal to minus 2a1, so it is minus 2 divided by root 6. All three coefficients for psi 3, that is the degenerate system, we got. And we can write the wave function as 1 by root 6 psi pz1 minus 2 by root 6 psi pz2 plus 1 by root 6 psi pz3. So all three molecular orbital wave functions we have determined. Okay. We got the energy of the wave functions of the cyclopropenyl system and we got the eigenfunctions for these systems. Now, if once you have the wave functions, there are ways to represent these wave functions for the cyclic system. Okay, and we need to calculate again the electron density, charge density, and bond order for this particular system. So, cyclopropenyl system we will be continuing in the next module also, and we have got, for the time being, we have got the wave functions of psi 1, psi 2, psi 3, and we have got the energy for the three energy levels. Okay, thank you.